Okay, so let us keep on studying the sequences, the algebra of convergent sequences. And the next theorem is not exactly about the algebra of convergent sequences, but about another feature which is extremely important, which is the boundedness. Okay? And so we introduce a definition here. We say that a sequence AN is called bounded if there are two numbers let me call them L1 and L2 such that real numbers for every n. This is not eventually, even though we could say eventually nothing changes, but don't let me say eventually now. For every n natural number, an lies between L1 and L2. Okay? Or, equivalently, if there is a number L larger than 0, such that for every natural number, the absolute value of the generic element of the sequence an is less or equal L. Okay? So this means pictorially that there are these two numbers that can be L1, L2, all minus L and L. This is L1, this is L2, and all elements of the sequence lie here in the interval L1, L2, A1, A2, A3. Okay? So, theorem. A convergent sequence is always bounded. Okay, and here we can immediately understand why, if we keep on having a clear picture of a sequence on the real line. So I really suggest you to keep in mind the real line and always to have pictures in mind. When you gain this ability, then everything will be much, much simpler. So what is a convergent sequence? A convergent sequence is something that eventually is close to some L. So convergent sequence starts from some A0, then A1, A2, and 3, and so on and so on. But eventually it concentrates around L and gets closer and closer to L. So, regardless of the behavior of the first elements of the sequence, it is clear that the sequence cannot escape to plus infinity nor to minus infinity. Okay, this is the idea. What is the problem, the conceptual problem of this theorem? The conceptual problem is that a sequence has infinitely many elements. So it is not so immediate to say that this collection of infinitely many elements remains in a bounded region. The point is that eventually the sequence is here in an epsilon neighborhood of L, but eventually means that here there are infinitely many elements. So we must use this eventually in the proof of this theorem. This is just to give you a hint of what is the spirit of this proof. And then the proof is very simple, but it is not so immediate for you. I guess that you in the high school already learned the proof for the theorems of the algebra of limits. Okay, this belongs sideways to the algebra of limits, but it is not completely adherent to the spirit of this proof. So I suggest you to follow this proof because it can be instructive for you. Okay, consider a convergent sequence AN that goes to the real number R, converges to the real number R. Okay? Now, take epsilon. Epsilon can be whatever positive number we want. So we fix epsilon, for instance, equal to 1. We fix it. Okay? Then, by definition of limit, there must exist some n bar, natural number, such that eventually after n bar, n larger than n bar, we have that an lies at a distance from L which is less than 1. This means that the n must lie between L plus 1 and L minus 1. So notice that in this way, what we did, we took into account infinitely many elements of the sequence, all the tail of the sequence, because n larger than n bar are infinitely many elements. So now we have to deal with finitely many elements, those that are before n bar. Okay, let me go further, and then we'll try to get back and to explain you a bit deeper what is the spirit of this proof. So now consider this set. Let me call it A, defined as the set of the following numbers: L minus 1 and L plus 1, that are used here to bound an infinite tail of the sequence for n larger than n bar, and then the other elements. So A naught, sorry, this comma is very awful, A naught, A1, many dots, then up to A n bar. Okay? So first, notice that A, capital A, is a finite set. Finite set. As it contains how many elements? So here we are from A naught to A1, so there are n bar plus 1, and then there are two others elements, so it has n bar plus 3 elements, which is a finite number. So since it is a finite set, it has a maximum and a minimum. When defining maximum and minimum, we specified it. I told you, if you have a finite set, a set made of a finite number of numbers, of real numbers, then there is maximum and the minimum. When it is infinite, it is not sure. But it is finite, and it has maximum and the minimum. So use the notation small m is the minimum of A, capital M is the maximum of A. Now we prove our thesis now that for every natural number n, an is contained in the interval between small m and capital M. So an is bounded for every n. Okay? First case is suppose that we consider an for n larger than n bar. Then as we already proved here, by choosing properly epsilon equal to 1, we have that an lies between L plus 1, and here lies between, L minus 1 and L plus 1. But L minus 1 and L plus 1 are elements of A. So L minus 1 cannot be lower than the minimum, and L plus 1 cannot be larger than the maximum. So as a final result, here we have that an, is between small n and capital N. So for n larger than n bar, this is verified. First. Second, suppose n is not larger than n bar. Then directly we have that this an here belongs to A. And as it belongs to A, it cannot be larger than capital M, nor smaller than small m. Okay? So here at points 1 and 2, we covered all cases. The first case, in which n is larger than n bar. The second case, all the residual case. So finally, for every natural number n, we have that an is between small m and capital M, and by definition of bounded sequence, we conclude that an is bounded. Okay, and so I want to go back to this. I want you to understand this proof. Okay, it's a good exercise in order to enter into the logic of the proof. What we did, it is just more or less as the first picture I gave you about this theorem, but I want to be more specific here. So we started from convergent sequence. An converges to L, then this means that eventually all elements of the sequence fall here in this interval between L minus 1 and L plus 1. Here we trapped infinitely many elements of the sequence. Outside this interval there is A0, there is A1, A2, and then up to An bar. But outside this interval there are just finitely many elements. So in set A, I collected A0, A0, A1, A2, up to An, and then these two numbers, L minus 1 and L plus 1. These two numbers trap infinitely many elements of the sequence, and outside there are finitely many. So there is a minimum, which here in the picture is A0, so this is minimum, and a maximum. And all the sequence is trapped here. We just use the hypothesis of the convergent nature of the sequence. Okay? Why did I prove this theorem here? Because we will use it for the second theorem of the algebra of the limits, which is the theorem about the product of limits. So the hypothesis is exactly the same as the hypothesis of the theorem about the sum of two convergent sequences. Then you are given two convergent sequences, An converging to L, real number, Bn converging to K, real number, and then Cn defined as the product An by n converges, is a convergent sequence 2, it converges to the product Lk. And here the statement is the limit of the product is the product of the limits. To give you the proof, so again we start always with the same statement, same sentence, which is let epsilon larger than 0, an arbitrary number, then since an goes to L, there exists a number n bar 1 in N such that when we are beyond n bar 1, the distance between an and L is less of what? Epsilon prime. Give me now the license not to specify what is epsilon prime. Epsilon prime is a positive number to be specified later. Part of the proof will be to be able to define epsilon prime as a positive number. Okay? You don't understand now? Just trust me. It is very standard, but we are not so used to that, but it is extremely standard. So, analogously, since Bn converges to K, there exists n bar 2 in N such that after n bar 2, Bn minus K is less than n epsilon prime. As usual, we want these two statements to hold together, so what we do is to define n bar as the maximum between n bar 1 and n bar 2. And in order to make these two statements hold together, we must choose n larger than n bar, whatever n. And then we start with the computation. And we have Cn minus Lk. This is equal to An Bn minus Lk by definition of Cn. And now we do the following trick. We add and subtract the same term. Why? Because it works. It will be clear later. So we subtract Ank, then it is the first sequence times the limit of the second sequence, and then we sum it again. So nothing changes, but these two terms will provide us the comfortable way to collect terms. The comfortable way is the following. So we have here An that multiplies Bn minus K. Sorry, I want to use the inequality after, plus K An minus L. Now the situation is nice here because we want this guy here to be small, less than epsilon. And here, by adding and subtracting these two terms, we provided here a couple of terms that are small, because here Bn tends to K, so this difference will be eventually small, and here An tends to L, and also this difference will be eventually small. We have to organize this computation in such a way that this becoming small is apparent. So let me just do less or equal here and use the first triangular inequality, and here we have An Bn minus K, absolute value, plus K times An minus L. And now we use this property of the absolute value, which is x, y, absolute value is the product of x y. So the absolute value of a product is the product of the absolute values. And so we have here an, absolute value, bn minus k, absolute value, plus k, absolute value, an minus l, absolute value. Now, here everything is good. This will be eventually small, this is fixed. Here, this is eventually small, but this is not fixed. This is a sequence. But we know that since an is convergent, we can say that an is bounded. This is very good. What does it mean? It means that there exists m larger than 0 such that an modulus is less or equal m. So the difference Cn minus Lak that I just not computed but just estimated, because here there is not an equal, so it is not a computation, it is an estimate. So this difference, this distance Cn minus Lk is less or equal this guy here, but now absolute value of n is less than this m, so we have that this is less than capital M times bn minus k plus k an minus l. Now we go back. What is n? N is larger than n bar. N bar is the maximum between n bar 1 and n bar 2. N bar 1 and n bar 2 are the label after which these two distances, an minus l and bn minus k, are less than this epsilon prime, to be still specified. But now these two statements hold together, and so here we can write that this is equal to m plus epsilon prime plus absolute value of k epsilon prime, and this is equal to m plus absolute value of k epsilon prime. Good. And now we want to specify epsilon prime. Remember that we want this distance to be less than epsilon, to apply the definition of limit. In order to make this guy here less than epsilon, that will provide that also this distance is less than epsilon, we can just define epsilon prime as epsilon. Sorry, here there is a strictly less. I'm sorry, here is less or equal, here is strictly less. This is epsilon divided capital M plus absolute value of k. Notice that this is larger than 0. Why? Because epsilon is larger than 0 and capital M is strictly larger than 0. Here it is written by definition of boundedness. This is good because k could be 0. K could be 0. We cannot exclude the 0 point from here. But since capital M is larger than 0, this ratio is meaningful, and epsilon prime is really a positive number. So now if you want, we can go back. We say, now we have epsilon prime. We could write it from the very beginning, but from the very beginning it sounded like magic. I prefer to give you this version of the proof in which epsilon prime is found from the proof itself. But now we have epsilon prime, which is a very legal positive number. So all passages here are justified. I ask you to trust me here. Now you don't need to trust me. It is true. Epsilon prime exists, that it is larger than 0. And now I know what it is. Since I know what it is, I can say that then the difference between Cn and Lk, which is less than this guy here, thanks to the definition of epsilon prime we finally provided is less than epsilon. So what we proved? We proved that for every n larger than n bar, for every n larger than n bar, the distance between Cn, the product of the two sequences, and the product of the two limits is less than epsilon. Then, by the definition of limit, we have that Cn converges to Lk. Okay? And this is the end of the proof. I suggest you to study this proof very well, to understand this logic and this fact that epsilon prime is defined at the end. And now I'll give you a corollary that sometimes is a theorem by itself that says you have a convergent sequence, an goes to L, C is a real number, then C times an is equal to L times C. So this is the limit of a sequence by a constant multiplied by a constant is the limit of the sequence by the same constant. It is a corollary of the previous theorem because we just define sequence Bn, which is equal to C for every n. So this is the constant sequence. The raindrop that falls always in the same point. And then, of course, Bn converges to C, the constant sequence converges to the same constant. Then, the sequence C times an is equal to Bn times an, because Bn is equal to C, and this converges to L by C by the previous theorem. The limit of the product is the product of the limits. This is the end of this proof, and this is the end of this video. We go to the next video.